Okay, let's give this a shot. I guess you can try this on your screen, and if you have some trouble, I'll give you some help.
Okay. I have no idea if this is anywhere close to right, but that's what I'm going with.
Okay, let's see. All right, I'm going to go back to my screen. So what's the graphical interpretation of this expression?
It's the area that's between the x-axis and the function between -3 and 5.
That's right. Now, this is a curve, so it might be difficult to figure out that area. So how are we going to try to figure out that area? Well, we've learned an approximation technique, which is draw a bunch of little tiny rectangles.
Mm-hmm.
Now, the approximation will be better if we draw lots and lots of rectangles. So what's our symbol for the number of rectangles?
N.
And then what are the names of the rectangles? Well, there's rectangle 1, rectangle 2, rectangle 3, rectangle 4, rectangle 5, all the way up to n. So let's say that we just want to talk about some arbitrary rectangle. What's our symbol for the arbitrary rectangle? The symbol is I. Let's say this is the ith rectangle. So what's going to be the width of that rectangle?
It's going to be 5 minus -3 over n.
Okay, good. That's right. What's our symbol for that width?
Delta x.
That's right. But what you said was a good definition. The width of that rectangle will be this, the total width divided by the number of rectangles. Now, how are we going to find the height of the rectangle? Well, first of all, we have to pick a sample point inside of the rectangle. We have to pick a sample point inside the rectangle. What's our symbol for the sample point inside the first rectangle? x1. What's our name for the sample point inside the second rectangle? x2. What's our name for the sample point inside the fifth rectangle? x5. What's our name for the sample point inside of the ith rectangle?
xi.
Right. We want to give a kind of general expression so that we're not just talking about just one rectangle. So we call this sample point xi. Where is the sample point going to be? Is it the left endpoint, the right endpoint, the midpoint? Well, we talked about last time, it doesn't make any difference. You can use any sample point inside the rectangle because all we're trying to do right now is get an approximation to the total area. Well, any sample point here will help us to get an approximation. What's the point of the sample point? The sample point is what's going to determine the height of the rectangle. The sample point is what's going to determine the height. We already know the width. This is what's going to determine the height. So what's the name for the ith sample point?
The name for the xi.
Right. And then how can we figure out the height of the rectangle, of the ith rectangle?
we can plug xi into the function if we're given one.
Good. That's right. So what would be our name for the height of the ith rectangle?
G of x.
Good, except g of x wouldn't be specific. In this case, the height would be
G of xi.
right. And it's always good to label that. Now remember, in reality, there would be many, many rectangles here, maybe 40 rectangles, but I'm only drawing one of them, because if we can just draw one, we get the basic idea. So the height here, so the sample point is the point we're figuring out the height above. If you wanted, it looks like I'm kind of using the midpoint here, but you could just as well have used a left or a right endpoint or any point. So that's going to be the height. So how would we calculate the area of the ith rectangle? What's the expression for the area of the ith rectangle?
Xi. Delta x times g of xi.
Okay, that's good. That's good that you took your time and figured it out. It's good you took your time and figured it out. So the width is delta x. The height is g of xi. So xi doesn't appear here separately. We're just using it to find the height. So this is the area of the ith rectangle. This is the area of the ith rectangle. So to review, what does this expression stand for?
That's the area of the ith rectangle.
Right. What does this expression stand for?
That is the width of the rectangle.
Yeah. We don't have to say delta xi because all the rectangles have the same width. And what does this expression stand for?
That is the height of the ith rectangle.
That's right. And what's this symbol stand for? That's the sample point in the ith rectangle. This is the sample point in the ith rectangle. What's the sample point? The sample point is the point we're using to figure out the height, as you can see. All right, now that only tells us the area of this rectangle. Remember, we want to know the total area under the whole curve from -3 to 5. So what we need to do is we need to add up all the rectangles. I only drew one rectangle, but there would be tons of them, right? There would be tons of rectangles all over the place here. So what would be the symbols we would use to show that we're adding up the areas of all the rectangles?
The sum sign.
Good.
And then on the bottom you put x. No, never mind. I forget.
So this is the expression for the ith rectangle. So what would be the area of the first rectangle? It would be this, right?
Mm-hmm.
And then we want to add this, right? Then we want to add this, right? And then what's the area of the last rectangle?
G of x n times delta x.
So this is what we're trying to do.
Mm-hmm.
That's what we want the sigma. So what's changing here? We're going from x1 to x2 to x3 to xn. So what's our the thing that's changing here is the subscript. What's the variable that we're using for that subscript?
The variable for that n.
Actually, what the variable we used here was I. We used I to stand for all the various possibilities. Here I is 1, here I is 2, here I is 3. So what would I be for the first rectangle? 1. What would I be for the second rectangle? 2. What would I be for the seventh rectangle?
7.
What would I be for the last rectangle?
The last value.
And what's our symbol for that?
N.
Right. So what would I be for the last rectangle? N. What would I be for the first rectangle?
1.
And what would I be for the last rectangle?
N.
So what we want to do here is we say we're going to add up all these terms, changing I each time. We're going to add up all these terms, but each time we're going to have a separate I. What's the first value we're going to use for I?
1.
And what's the last value we're going to use for I?
N.
Okay, so that's what these symbols mean. If we understand what they mean, we don't just have to memorize them. We can actually figure out what this makes sense. So do you see how this expression now makes sense? This expression is a shorthand for this. This is a mathematician's shorthand for saying, well, first add g of x1 times delta x, then add g of x2 times delta x, then add g of x3 times delta x, then add g of x4 times delta x, and keep going until finally you add g of xn times delta x. This is just a shorthand for this expression. So the variable we're changing here is I. We're changing the subscript. We're changing from I of 1 to I of 2 to I of 3 to I of 4 to I of 5. So here's the variable we're changing. Here's the first value of the variable, and here's the last value of the variable. That's how this notation makes sense. Okay. So that would be the notation we would use here in this case. So do you see the distinction between I and n? I stands for any rectangle. I stands for any subscript. N stands for the last subscript. I stands for any subscript. So I goes all the way from 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to n. But n just stands for the last subscript. I guess it's kind of a weird notation. It takes a little time to get used to it. So anyway, what does this mean? This means adding up the area of all these rectangles.
Okay.
This means adding up the area of all these rectangles. Now that still wouldn't be enough though, because that would only give us an approximation to the area under the curve. The rectangles are only approximating the area under the curve. How could we figure out the exact area under the curve? Well, how could we make this approximation better? How could we make this approximation better?
We use, we use more rectangles, so a ton of rectangles.
That's right. We could make this approximation better by increasing the number of rectangles. And what's our symbol for the number of rectangles?
N.
Right. So how could we make this approximation bigger? Use a bigger n. We can make this better by using a bigger n. How could we make it give the exact right answer? How could we make it give the exact right answer? By taking the limit as the number of rectangles goes to infinity. What's our symbol for the number of rectangles?
N.
Okay, so I think this is the answer we were going for.
Okay,
Or this is the first part of the answer. And again, if we understand this, then we can figure it out if we start to forget it, or it'll help us to remember it anyway. If you just rely on brute memory, then it would be easy to get symbols confused. For example, should this symbol be n? Well, that doesn't make any sense. N can't be 1. I is going from 1 to n. And would this symbol be I? Well, that doesn't make any sense. Here we want to have the number of rectangles that's going to infinity. So if we understand the symbols, then we should see how each of them has kind of ended up in the right place, although I guess it is kind of a weird notation. So we're taking the limit of the Riemann sums, this right here. This here is what's called a Riemann sum, right? This is a Riemann sum. We're taking the limit of the Riemann sums as n goes to infinity. The Riemann sums approximate the definite integral. When n is big, the Riemann sums are a good approximation to the definite integral. And in the limit, as n goes to infinity, the limit of the Riemann sums as n goes to infinity would give the exact value of the definite integral. That's the long way of finding the definite integral. Okay, now there's still some more stuff we need to add here. We need to tell the reader how to find delta x, and that's something you already knew. You already told me.
Mm-hmm.
Notice we're not dividing by I here. We're dividing by the total number of rectangles, n. And there's something else I forgot to mention last time that we should also say. We have to tell the reader what xi means. Remember what xi is? Remember xi is called a sample point.
Right.
What does that mean when we say it's a sample point? We mean that it's a point inside the ith rectangle. This means a point inside the ith rectangle. Otherwise, the definition doesn't really define anything. So xi will be a point inside the ith rectangle. It's the point that we're using to find the height of the ith rectangle. This is the point that the coordinate that we're using. Maybe I should say this is a coordinate inside of the ith rectangle. It's the coordinate we're using to find the height of the ith rectangle. Okay. Okay, so this would be the answer. Okay, so we hadn't really practiced this much last time. So the answer that you were putting on your screen, I think you can see now, there was definitely some mistakes with that. Notice that we don't really, where did the 5 and the -3 come into it? They only came into it here. The only place the 5 and the -3 came into it was here. They didn't come in here with the limit. Now, it would be nice if we could be more specific and plug an actual expression in for g. But in this case, that's not possible because they didn't tell us what g is. Right. So if they had given us an expression for g, we would take the next step now and plug an expression in for g. But since they didn't give us an expression for g, we just have to stop right here and just plug in the name. So if all they give you is the name of the function, all you can write down here is the name of the function. But if they actually gave you an expression for the function, you'd actually have to use the actual expression for the function here to be as specific as possible. Okay, so I think now this is the answer. Notice that they did say don't evaluate the limit. It would be, so all we have to do is write this down. So this is basically the definition of a definite integral. Okay, all right. Is that making any sense?
Yeah,
all right.
Yeah, it makes sense now. I was a little confused, I guess.
We didn't really practice this last time, so now's the time for us to go over that. All right. Let's try this problem. I guess you can try this on your screen.
Oh. Okay, and then we add up the sum of as xi equals 1, xi is 1, and our function is h of x. Okay.
Okay. Okay, good. Now, actually, I think now we should go on and actually do the calculation. What is -3 minus -10?
Okay. That is -3 plus 10, so 7.
So I guess that's what we should have in our final answer.
Okay.
We hadn't done that before. Okay, now I noticed that off to the side you defined what xi means. Let's see. Okay, I'll go back to my screen.
Okay.
Do all of these rectangles have the same width?
Yep.
That's why we don't need, so do you see, that's why we don't have to call this delta xi. We would call this delta xi if each delta x was different. But since all the delta x's are the same, we can just call them delta x. That makes sense?
Mm-hmm.
Do all the rectangles have the same sample point?
No.
So should this be x or xi?
Xi.
All right, but actually when you did it, you wrote it as x.
Okay.
So this should actually be xi. And I was trying to give you an explanation so we can understand when we use the I and when we don't. We use the I for the parts that are different in each term. Each term is going to have a different sample point, so we need an I to show that each sample point is different. Each point is going to have the same width, so we don't put an I in here. Remember what this really stands for is how would we figure out the height? So what's going to be the name of the first sample point?
X1.
Excellent. So how do we figure out the height of the first rectangle?
We plug X1 into the function.
So what goes in this parenthesis?
X1.
Excellent. All right, and what's going to be the name of the second sample point?
X2.
And how do we figure out the height of the second rectangle?
We take h of X2.
Okay, good. So notice we don't, this is supposed to be a shorthand for this. We don't need an I for the delta x because the delta x's are not changing. We need an I for the subscripts to show that the subscripts are changing. What's the first subscript?
1.
So it starts at 1. And what's the next subscript? 2, then 3. And what's the last subscript?
N.
All right, I didn't write this right, but I think you wrote it right. It's supposed to be an N. Okay, hopefully you wrote that right. Anyway, that should be an N. Okay.
Yeah, I guess I should change changes. Okay.
Yeah, you did write it as an N. That's correct. Okay. Let's stay on my screen for a second because there's another important change to make.
Okay.
All right. So this then here is a 1. Then it's going to be 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What are we plugging in the 1 into? What variable are we plugging the 1 into?
I.
I or xi?
I.
So this notation that you used was incorrect. If you see, you wrote it as xi. So what would this mean? What would it mean the way you wrote it? The way you wrote it, it would have meant this.
Okay.
If you see the distinction between those, the way you wrote it, you said we were plugging the 1 in for the xi. You were basically saying we're plugging 1, you're plugging 1, 2, 3, 4, 5, 6, 7 in for the sample points. But 1, 2, 3, 4, 5, 6, 7, those are not the sample points, they're just the subscripts for the sample points. So we don't want to say that the xi is going from 1 to n, we want to say that the subscripts are going from 1 to n. I guess it really is kind of a weird subtle notation. It takes a few tries to get used to it. But again, hopefully if we understand it, it'll be easier to remember it. Okay, so the way you wrote it, we would have been doing this sum, but that's not actually the sum that we want. Okay, and I think it would be good to add this as well. When we say what xi means, remember there's going to be n different sample points. So rather than just saying xi is a sample point, we can say xi is a sample point in the ith rectangle. So I think this will be the best type of answer we can give. Xi is a sample point in the ith rectangle. So notice, does I stand for an x coordinate? Does I stand for x coordinate? No, I is the subscript on an x coordinate. I is the subscript, but it doesn't stand for the coordinate itself. I guess this is pretty tricky notation. Okay, so let's study this for a while. So where did we go wrong here? First of all, the thing that we're, there were two problems. One problem is, at first we wrote this as an x, but if we just write it as x, that makes it be the same in every term. Since we want this, the subscript is the thing that's changing in every term, so it has to be marked with an I. We're using I for the thing that's changing in each term. We're using I for the thing that's changing in each term, so this has to be an xi, not just an x. And the other thing that went wrong was at first we had written this as xi equals 1. But that makes it seem like we're plugging in 1 for the x coordinate. We're not plugging in 1 for the x coordinate, we're plugging in 1 for the subscript on the x coordinates. So there's pretty likely to see a problem like this in the test, and you can be sure since they're relatively simple questions, they're going to be grading to get it exactly right. So those are some of the details we need to get that exactly right. Okay, is that making sense?
Yep.
All right.
Okay.
Okay, I'll go back to my screen. Okay, by the way, something I hadn't mentioned, but we should probably get into the habit of writing it like this. This limit equals the definite integral. So it might be good if we start labeling that that's what this is. This is the long way, this is the definition of what the definite integral means. Okay, so what does xi stand for?
It's a sample point of the ith rectangle.
Great. So what does this term stand for?
That's the height of the rectangle.
The height of the ith rectangle. Good.
Right.
And what does this term stand for?
The width of all rectangles.
Yeah, the width of the ith rectangle or of any rectangle. So what does this term stand for?
The area between 2 and -5 of the function.
Now that answer was mistaken. This term right here is only the area of the ith rectangle. This term here, do you see why? We're just taking the height of the ith rectangle times the width of the ith rectangle. So this term here is just the area of the ith rectangle, if that makes any sense.
Mm-hmm.
Then what does this stand for? This is the area of all the rectangles put together. If you see the distinction,
Yep.
This is now the area of all the rectangles put together. And what does this stand for? This is the total area under the curve. This is the total area, because if you take the limit as the number of rectangles goes to infinity, that gives you the exact area under the curve. Okay. Something I should say is sometimes your instructor uses a star
Yeah, I saw
for
that.
sample points. So I would say probably whether you use the star or not is optional. You can use the star, but looking at the answer key, they don't always use a star. So it looks like that's optional. So you can either use a star or not here. However, you cannot put a star here. I want to emphasize that. So can you put a star inside the sigma notation? Yes. Although I think it's optional. Can you put a star inside the integral notation? No. So to review, can we put a star inside the sigma notation?
Yep.
Yeah, although it's optional. Can we put a star inside the integral notation?
No.
No, that's not the correct way to write it. Notice even if you put a star here, you wouldn't put a star here, right? Because the star means sample point, and this is not a sample point. So the only place that you might put a star is here. You wouldn't put a star here. The only place you might put a star is here. That would be optional, but it would be wrong to put it anywhere else. Okay. Now, how about... Okay, yeah, I think that's good enough. Okay, so I had some extra comments on this, but your answer was correct. I made some extra comments, but your answer to this problem was correct. That's good. Okay, now let's try this problem. So we got that last problem right, so now we're moving on to something that's a little different. This is a little different from the problems we've done before, but it's not super different. We should be able to figure out what they're going for here. But anyway, well, let's give it a shot. So this is a little different from before, but we should be able to use what we've talked about to get an answer to this. So give this problem a shot.
Okay. Okay.
Okay, I'll go to my screen. Okay, this is what you wrote down. So this was good. This was excellent. We haven't done this before, but you figured out exactly what the problem was going for. Basically, it looks like you figured out this is just the reverse of the earlier problems, right? Here we saw that this term is equal to this term. Well, if the integral is equal to a limit, then the limit is equal to an integral. So they could test it either way. They could give you the integral and ask you to write it as a limit, or they could give you the limit and ask you to write it as an integral. So you figured out that's what they were going for here. That's good. So when do we use the star? Sigma notation or integral notation?
The star is for sigma notation.
So one thing you did was good is you didn't put a star here. I'll bet a lot of students would make that mistake. So it's good that you put no star here. And when do we use the subscript I? Do we use the subscript I for sigma notation or integral notation?
Sigma.
So again, something that I bet a lot of students would do is this. But that's wrong, so it's good that you left that out. We don't need any any subscript here. So you avoided some traps and did that exactly correctly. Okay, good. So the point here is that your instructor just wants you to know that this is the definition of a definite integral. A definite integral is the limit of a sum. The definite integral is the limit of a sum. By the way, now you can start to see why this notation makes sense. This is called the integral sign, but an integral sign is just a long S. The reason why they use an integral sign is because integrals are sums. So this is to see, we can see these are use the integral sign as a long S. The S stands for a sum because it comes from the sigma. And also, we never really explained what this dx means, but you can see it's kind of standing in for the delta x. The dx here is in the same position as the delta x over here. Now, we're not going to go into a lot of detail about what exactly that means, but you can kind of see why there's some sense into putting a dx here. It's in the same position as the delta x in the original expression. Okay, that's good enough for that. We don't have to go into too much detail about that. But anyway, you saw the correct way to write this out. Okay, good. So that's another variation on the types of questions they might ask you. You worked that out. Good. Okay, let's try that problem.
Okay, so we use the xi up here as the input into the function as the sampling point to find the height. We use the sample point to find the height of the function, the height of the rectangle. And to find the height of the rectangle, we need to plug in the sample point into this function. Okay.
That's true. That's true. That's a good analysis. Good.
So we have to plug it into both x values. Okay, so I think this is good then.
You're right. So there were two different places that we had to plug it in. That's a good analysis. I think you probably need to also put in parentheses, though, to show that to show the delta x is multiplied times both of those. This is a little confusing. You don't need the parentheses for the integral. The parentheses are kind of just understood in the integral. We don't need parentheses in the integral, but we do need the parentheses in the sigma notation. Otherwise, it looks like you're only multiplying the sign times the delta x. So that's something to watch out for there. We hadn't seen an example like that before. And then those stars are optional, so it's not wrong to put them in. But if you do put them in, you better put them in on your explanation down below as well, so that you're consistent. Okay, so that's optional, but if you do put in the star, you have to be consistent and put it in everywhere. Okay, well, it looks like you basically figured this out. That's good. Let's talk about that for a moment more. So notice, what type of notation do we use the I for? Integral or sigma?
Sigma.
And how about the star?
Sigma.
How about delta x?
Sigma.
How about dx?
That's the integral notation.
Right. I noticed that there was one moment when you were writing the dx for the sigma, and then you caught yourself. So that was good, but I just wanted to emphasize that. Delta x kind of stands for the same thing as dx, but we still have to use them in the correct places. Dx is the symbol with the integral notation, and delta x is the symbol with the sigma notation. So you did that correctly. I just wanted to emphasize that. Okay, so that was a good job working that out. I'll go back to my screen.
Okay.
Okay, I'll just copy part of this here. Good. What did I want to say? So one point is, so what does xi stand for here? What's xi?
A sample point of the ith rectangle.
And what does this term stand for?
That is, let's see. That's the function. So that's the height of the ith rectangle.
Yeah, that's the height of the ith rectangle. And what's this stand for?
The width of the ith rectangle.
Or of any rectangle. That's right. So what does this term stand for?
The area of the ith rectangle.
That's right. That's the area of the ith rectangle. So what does this stand for?
The sum of all the rectangles.
Yeah, the area of all the rectangles. So what does this stand for? Well, in the limit, this now stands for the actual area under the curve. This is now the actual area under the curve, or as you were going to say, the definite integral. Okay. So so you can see the definite integral is really a pretty complicated, difficult idea. That's why this is one of the big accomplishments of calculus, to work this out. Now, in some courses, the next step would be to actually evaluate this limit to figure out the definite integral, but your instructor is not requiring you to do that. You do know how to figure out this definite integral the short way, though, using antiderivatives. You could figure this out the short way using antiderivatives, but we don't need to do that on this problem. Now, wait a second. We did some problems earlier where we drew curves, and then we drew a whole bunch of rectangles. And we actually calculated the area under the rectangles, right? We did earlier problems where we actually calculated the area bunch of rectangles. How do you know when they want you to solve it this way, and how do you know when they want you to solve it this way? How did we know in this case that they didn't actually want us to actually draw the rectangles? How are they going to express it differently? Well, the key thing here is this is a way of approximating the integral. If they ask you to approximate the definite integral with a specific number of rectangles. When the problem says to approximate the definite integral, and then they tell you how many rectangles to draw, like 3 or 4 or 5, that's when you should use this method of solving. We haven't done that today, but we did this in the previous sessions, right? So when the instructions look like this is when they want you to actually draw the rectangles and do it using the previous method. On the other hand, when they tell you to actually express the definite integral, notice they're not saying to approximate it, they want us to express what it really is. That's when we use this approach. Also, another clue is notice here they use the word limit. Obviously, this approach doesn't involve a limit. So when they use the word limit, that's another clue that they want us to solve, that they want this type of answer and not this type of answer. Okay, so I'm just trying to give you some clues so we can know when to use this type, when it's this type of problem, when it's this type of problem. I just remember there's two different types of problems. If you remember there's two different types of problems, we should be able to figure out the difference between them. Okay, good.
Should it be, instead of n equals 1, should it be I equals 1 with n on top?
All right, well, you know you're picking it up when you can catch the mistakes. Excellent, very good. That's right, that's my mistake. Thanks, that's how I should have written it. Okay, so let's try this problem.
So we express this. Let's see. Okay.
So one thing you did here is on the left hand there was an I, but you didn't use I for the integral notation. That was good. And in the left-hand side, there was a star, but you didn't use the star for the integral notation. That was good. I noticed that you were a little unsure about the limits of integration. Those numbers are called the limits of integration. Well, how do we figure it out? Which number goes on the bottom, the smaller or the bigger limit?
The smaller.
And which number goes on the top?
The larger.
Okay, so you ended up with figuring out correct. So that you ended up with the correct way to write it. You wrote it correctly. The smaller number goes on the bottom and the bigger number goes on the top. There's actually some exceptions to that. Your class isn't covering that. In your class, the smaller number always goes on the bottom and the bigger number always goes on the top. And that's what you ended up with there. Okay, that's excellent. Great. I'll go back to my screen. So that's another variation on the types of problems we've seen. Notice that this problem was actually kind of lazy. This problem was lazy. They should have said that delta x equals 8 divided by n, right? But they're just taking it as understood. And they should have said that xi star is a sample point in the ith rectangle, but they're just taking that as understood. So the instructor can afford to be lazy when they're writing the test problems, and you're just expected to assume that they meant to say those things even though they didn't. But when we write our expressions, when we write it this way, we have to express the definition of delta x as 5 minus 3 over n, and we have to define what the xi means, even if the instructor doesn't always do that in the problems. Okay, good. All right, so I think we made some progress on understanding that. So the purpose of this is just to give you a little bit of an inkling about what definite integrals mean. Mm-hmm. What they mean is approximate the area by making a bunch of little rectangles and then take the limit as the number of rectangles goes to infinity. So it's a pretty subtle, complicated idea, but the instructor's hoping that you'll get a little bit of a sense of what the definite integral actually means. Okay? Okay, let's try this problem.
Okay. New canvas.
That's a good idea.
Y equals x squared plus 1. That's the best I can do.
Okay.
Oh, it's terrible.
Did you get that from your graphing calculator?
Yep.
Okay, that's good. That's a good idea.
I have bad handwriting in general, and then the tablet just confounds it. Okay.
Well, just do the best you can.
X is 2, Y is 5. 1, 2, 3, 4, 5. That's not anywhere near it. Okay, so X is 2, Y is 5, 3, Y is 10. So, alright, I'll do this. Using left endpoints. Definite interval. Approximate using Riemann sum. N equals 3 is enough endpoints from 0 to 3. Oh, I didn't even need to draw this. Okay. Function. Okay, so here's my first endpoint, 0, 1, and 2. So 1 times 1 plus 1 times 2 plus 1 times 5. 2 plus 1 plus 5, so 8. Let's see. This should be under the definite integral, so I'll graph this and see x squared plus 1, something in calc. 0 to 3. And the definite integral is 12. So this looks like it's right.
Okay, done?
Yep.
Okay. All right, that's an interesting idea to check it. Based on your picture, would you expect your answer to over or underestimate the area?
It would be under.
And did that match what you got in the calculator?
Mm-hmm.
So that's something else we can use to check. By the way, do you remember, how does your calculator calculate the definite integral? How does your calculator calculate this definite integral?
It uses the long way, which is the rectangle method.
Right. Although we wouldn't quite call it the long way. That when we use that term, the long way, we're saying that's the long way to find the exact value is to take the limit as n goes to infinity. But your calculator can't take limits. So what your calculator does is it doesn't take a limit. It just does exactly what you did, but with a really big number of rectangles.
Okay.
So the point is the calculator just does the same thing as you did, except it would split this up into maybe 10,000 rectangles. Because notice, does your calculator know how to do the calculations necessary for a Riemann sum? Well, yeah, they're really easy calculations, right? You don't need to know calculus to do that, and your calculator can do things really fast. It doesn't mind drawing 10,000 rectangles in its head or something like that. Okay, so your calculator only approximates the definite integral, but it uses so many rectangles, the answer comes out to be pretty much almost exactly equal to the true answer. It's in fact, when you round off, it comes out to be exactly the same. It's using so many rectangles. Okay. All right. Well, we haven't done a problem like this today, so it was good that you remembered how to do this. Notice how this is different from the problems we were doing earlier. Let me take another look at this. So it's good that you labeled this as R. R, because it's a Riemann sum. You made a nice, clear picture. Did you put dots in for your sample points?
Mm-hmm.
That was something that was giving us trouble in the past, remember? So it's important to put in those dots for the sample points. Okay, good. So that was a good process. That's a question you might see on the test. I'll go back to my screen. We got that correct. So notice some problems give you a graph, and some problems you have to draw your own graph. Actually, it wasn't the math here that gave you trouble. We just had a little trouble drawing the graph, partly because we were using the tablet. But here's some pointers when you have to draw your own graph. I think you kind of figured out some of this here on your own. It turns out that for this graph, we don't need the negative y-axis, and we don't need the negative x-axis, right? So we might as well have just done this quadrant. And then when you look at your calculator, you can see that the basic structure here looks like this. My advice then would be draw the curve first.
Okay.
And then put in the hash marks. And something else you figured, at first you were doing hash marks like this. But then you realized, why make the hash marks so close together when I only need 3 hash marks? So then you changed and you put the hash marks more widely separated. And that was a good idea as well, to separate the hash marks more so that you have more space for your rectangles. And then my other piece of advice would be now go in and label this axis. So we know here's 0, this is 1. And there for 1, this should be 2. And then for 2, this should be
5.
5. So I'll call this 3 and 4. See what I'm saying? Draw the curve first and then force the hash marks to match up. That's easier than drawing the hash marks first and trying to draw freehand a curve that matches up. And then we know this point is 3. Although actually you probably didn't even have to go this far for this problem, did you?
Nope.
But anyway, 3, that would be 10. So then you could call this 6, 7, 8, 9. So those are just some tips that make it a little easier to draw the graph. First of all, as you figured out eventually, we didn't need the negative x-axis. We don't need the negative y-axis on this problem. Make your hash marks as widely spaced as you can and draw the curve first and then make the hash marks line up instead of drawing the hash marks first and trying to make the curve line up. Okay, but overall that was a successful problem. You ended up with the right answer. That's good.
I had to close interval -2 to 3 into 5 equal subintervals. Okay. So
and you can zoom in as much as is helpful for drawing on that graph.
Okay, so first
Okay, good.
Okay, and then we need to.
So who says your instructor's not a generous man? You might notice that the delta x has always come out to be 1 in your class. So if you ever feel unhappy about the class, you can just remember that they're generously making all the delta x's come out to be 1 for you.
Okay, so 3. Okay. Okay, so now I'm using right endpoints. I met the function. I came over and down. I met the function over and down. I'm at the function. So I'm good. So now my next point, I meet the function. Now that's it. -1. Wait, so I'm using right endpoints. I meet the function. I'm at the function. I meet the function. Meet the function. Okay. Okay, so I did that. Now we do find the Riemann sum. R equals, so this is A, B, well, C, D, E. Equals 1 times the height, which is about 2.7 plus 1 times 2.
Okay, and let me give you a pointer here. So on these types of problems, when possible, try to interpret the graph so that the function values are integers.
Okay.
So for example, if you look more carefully at x equals 3, is there any way to interpret that? Is there any way to put the sample point at an integer? Notice when x equals 3, doesn't it actually really look when x equals 3 like you could easily say the sample point is at an integer? If you see what I'm saying, what integer is it at?
3.
So what I'm saying is we should have drawn a different rectangle there. We should have drawn the rectangle. So let's erase the top of that rectangle.
Okay.
That's what you'll need a smaller eraser. Probably very small. Okay, first put in the sample point. Remember, it's always actually, we should have done that for all the rectangles. That's the safest approach. First, draw the sample point. Put a dot for the sample point. Yeah, notice how you may as well assume the sample point goes straight through the integer value. It's a little bit ambiguous, but why not make your life easier for yourself? That's what the instructor is trying to allow us to do there. And then once we have that sample point, then we can go through and draw the rectangle.
Okay.
So the point is, if it's possible to interpret the function as having an integer value for the sample point, that's what your instructor wants you to do. I know we did do a problem earlier where it was clearly in between integers, but when it's possible to interpret it as an integer, that's the best thing to do. That's what your instructor is going for.
Okay. So this one's at 2. This one is at 1. Right. That one's at 0, sorry. That's B, that's C. B is 1 times -1.
Okay, now that that last rectangle E, that's another case where we actually could have interpreted the graph as crossing at an integer.
Okay, so would you say 0? Because I mean,
let's see here. One moment.
Maybe.
Go back to my screen.
Okay.
It's a little hard for you to see this because you've written over your graph. So take a look at what it looks like on my screen before we start writing over it. So remember, we're doing a sample point of x equals -1. So when the sample point is x equals -1, what should be the height of the rectangle?
1, I guess. I mean, but it just doesn't
Certainly
seem like
not 0. I'm not quite sure where you're getting the 0 from. It certainly doesn't seem to be crossing at 0 here. It looks like it's pretty darn smack dab right through 1 here. So it's a little hard to see on your picture because you've written on top of it. But if you look at the original picture here, it is crossing through 1. It's certainly a long way away from 0.
Okay.
Or from 2. So I can certainly see how you might call this. You certainly might say, well, maybe it's not 1, maybe it's 0.9 or 0.95 or 1.05 or 1.01. But why not make our life easier? The instructor probably means us to interpret it as a 1 in this case. It's certainly not going to be going through the 0 value. So okay, so that's on your picture. That's a little hard to see now because we have some writing over it. But if you look at the original problem, it's not too hard to see that it really is crossing at 1.
Okay, so we add these up and we get 3 plus 2 plus 0 plus -1 plus 1. And the Riemann sum is 5. And we can check this. We should get an overestimate. Well, actually, I'm not quite sure what we should get in this case. I'd say an underestimate, actually. Because this area between -1 and -2 is.
That's a good point. That shows some good intuition. Rectangle E, the right endpoint method worked very badly for rectangle E. Rectangle E is a severe underestimate, so we would expect our answer severely underestimates the true answer. That's right.
And we can't even, yeah.
But that doesn't do us too much good because since we don't have the function, we can't figure out the true value. So that was a good intellectual exercise. That was a good thing to think about. You're absolutely right. It looks like it's an underestimate because rectangle E is such an underestimate. But we can't actually check this answer. All you can do is just go back and double check your work. So notice how the instructor set this up so everything would be, all the values would be integers. I can't guarantee it'll be that way on the test, but if it's possible to interpret the graph as going through integers, that's probably what your instructor wants you to do.
Okay.
Okay, something you did here that was very good. You and I have never done a problem where we've never done a problem like this, where the function had negative y values. You and I have never done a problem where the function had negative y values, but you worked out on your own, or maybe you've seen other examples of exactly how to deal with that. You just plugged in the -1 for the height for rectangle D. So that was good. You just plugged in -1 for the height of rectangle D. We haven't talked about that before, but you worked out how to do that, so that's good. Also, oftentimes I think a student might get weirded out by the 0 rectangle C, but I think you handled that correctly as well. It's a weird rectangle with 0 height, but you handled that well. Let's zoom out a little bit so we can look at your calculations. Remember that when you do a definite integral means area under the curve, between the curve and the axis, right?
Mm-hmm.
But what happens when the curve is below the x-axis? Those areas are supposed to be negative, right?
Right.
But notice how that just comes out automatically here if you plug in the function value. Because what did you get as the area of rectangle D?
That was -1.
Notice how that came out. It automatically comes out negative because you're doing 1 times -1. So you can see that this definition of definite integrals using Riemann sums is automatically going to make the areas for the portions that are underneath the x-axis, it's automatically make them come out negative, which is just what we would want on that type of problem. Okay, all right, so the one issue we had here was, again, if it looks like you could interpret the function as crossing an integer, that's probably what your instructor wants. But otherwise, that was a good approach for that problem, a good, careful approach. So I think we can go on to part C.
Let's see. Okay.
So in part C, how many rectangles are there?
5.
No, that was part B and part A. Remember that in part B and part A, we were only approximating the integral. So we just used a small number of rectangles, 5.
Oh.
Parts A and B, we were only approximating, so we just used a small number of rectangles, 5. But now they want us to express the actual integral. That means the exact value of the integral. Well, so in this, as we're doing kind of a thought experiment. In this thought experiment, how many rectangles are there?
Infinite amount.
Let's see. That's probably not quite the best way to put it either, because infinity is not really a real number. If you tell someone, figure out the integral by drawing an infinite number of rectangles, that doesn't do them any good. Who knows what infinite means? So let's see. Just look at your sigma notation. In your sigma notation, how many rectangles are there?
N?
That's what I was going for. Yes. Okay. N rectangles, where presumably n is a big number. So in the sigma notation here, n stands for the number of rectangles that we're drawing. Good. And then we're going to take the limit as the number of rectangles approaches infinity. That's something that someone can actually do. No one can actually calculate the area of an infinite number of rectangles. That doesn't even mean anything. But you can calculate the area of n rectangles and then take the limit as n goes to infinity. How could you do that? You could use the tools. You could do that using the tools for limits that you studied in the first chapter of the course. Your instructor is not requiring you to do that, but that's something you could do. Okay, so what does delta x stand for in that expression?
It's the width of all the of each rectangle.
That was a good correction. It's not the width of all the rectangles, it's the width of each individual rectangle. Now you need to give the reader a formula for calculating delta x in the sigma notation. How are they supposed to calculate the delta x?
By taking 3 minus negative 2 and divided by 5. Oh wait, no, oops, that's wrong. N.
Okay. That's why I was asking you how many rectangles there were. That's why that matters. Okay, so we would have lost some credit on that part of the problem because we were mixing up part B and part C. We can't, so how can you simplify that expression for delta x? Just 5 over n. But notice it's not just one number, because as n gets bigger and bigger, what's going to happen to delta x?
It's smaller.
You can see that because n's in the denominator. So it doesn't make sense to say that the delta x is equal to 6, or the delta x equals 0.5, or the delta x equals 0.0005. The delta x doesn't equal any one number. The delta x is going to equal a different number for each value of n, and the delta x will keep getting smaller. Okay, so other than that, we got that correct. But this is the type of problem where the instructor is probably going to be pretty harsh unless on the grading unless we get every single part correct. Okay, so I can see why you wrote down that 5 there, because you were still thinking about parts A and B. So it's important to see the difference between A, B, and C. In parts A and B, we were only approximating the integral with a small number of rectangles, 5. In parts A and B, we were approximating the integral with a small number of rectangles, just 5. But in part C, they want us to express how you could actually find the exact value of the integral. Well, for that, you have to imagine having some arbitrary number of rectangles, n, and then letting n go to infinity. So how did it mess us up? To forget that, the only place where that messed us up was with the wrong denominator in the delta x, but I think the grader would be looking for that. So here we're now dividing by n. After all, in your sigma notation, you didn't say I equals 1 to 5, did you? In your sigma notation, you didn't say I goes from 1 to 5, you said I goes from 1 to n. So since you're assuming n rectangles, we have to put that in the formula as well. Okay, so that would be a good one to mark and go back and come back to. You're probably going to see a problem like that on the test. So the lesson here is don't mix up the approximation questions with the express the integral questions. Those are two different types of questions. I'll go back to my screen. Okay, so those are some problems from the website. Overall, we made some good progress on that. We weren't 100% on those. We were making some mistakes. But I'm not going to do any more practice on that with you. I think you can practice that on your own now, but you definitely should. You should definitely practice that some more on your own because right now we're not quite at 100% yet. So obviously, I'll try to do problems where you can check your answers. Maybe just redo the ones we just looked at. All right, we still have some more material to go to, though. So let's look at the next topic here. Those weren't 100%, but we certainly made a lot of progress on that so far. And I think if you work on that more on your own, you should be in good shape to get full credit on those on the test. Okay. Calculate the area here.
Okay. 1/2 of 8 times 6, so 24.
That's right. Okay. All right, that didn't give me too much trouble. Very good. Oh, I started out pretty good. All right, well, this was supposed to be a circle.
Right.
It started out pretty good. It started good, but then I got impatient. I should have drawn a smaller circle. All right.
Okay, the area of the circle is pi r squared, so pi 3 squared. So the area is 9 pi.
That would probably be the best answer because your instructor wants you to give exact answers, right? So rather than putting in for pi in the calculator, that would probably be the best answer. Good.
This area is the eighth of, okay, gotcha. Okay, so the area is pi 8 squared divided by 2, so 64 pi divided by 2. 64 pi divided by 2, which is 32 pi.
Okay, good. So if you know how to find the area of a circle, you should be able to figure out the area of a semicircle. Very good. And let's figure out this area.
Okay. The area is pi 5 squared. So 25 pi.
So I was trying to put in a trap here. The trap would be if you plugged in 10 squared. But 10 is the diameter, not the radius. So you used 5 for the radius here. Okay, good. So that's a little geometry we need here. Okay, tell me when you have that copied down.
Yep.
Okay, so they do not want us to work this out by using limits. We're not supposed to use the limits approach we were just talking about. And they also don't want us to figure this out using antiderivatives. This is a new method, interpreting this in terms of area. The first thing we need on this type of problem is we're going to need to graph the function.
Okay.
So let's pull over our calculator.
So we second catalog absolute value of x minus 5 graph.
All right, so it looks like you found the absolute value function. Great. Use the catalog. I don't usually use that. What happens when you do that? Oh, it's right there at the top. Very convenient. All right, good. All right, very good. By the way, well, you don't get better than that. But by the way, it's also, if you can see my screen, if you go to the math and then you go to number, it's here. Absolute value. But actually, it's probably easier just to go to the catalog. You're right. Okay, good. So anyway, we got absolute value. Oops. X.
Someone just showed me that today.
Oh, okay, excellent. These people keep stealing my thunder. Nope, that's good. That's good. It's good. All right. So that gives us this graph. So then the next thing you would do is draw your graph. How should I label this axis?
That's x.
And I guess we'll call this y, or maybe f of x. What's this point here?
That point is, let's see, trace 5.
So looking at it, it looks like 1, 2, 3. It looks like it's at 5, and then we can check that by tracing. How can you tell that that really is on the x-axis?
Because y is 0.
That's right. Okay, so that confirms that this really is 5. What's this point?
Let's type in x is 0, and we get y equals 5.
Good. You can also kind of eyeball it. 1, 2, 3, 4, 5. But the only way to tell for sure that's right is to put in x equals 0. And you can see it's exactly equal to 5. Good. Now there's one other point I need. How
9.
far out? How far to the right do I need to go?
To 9. So we can
9. That's right.
type in x equals 9, and it goes up to. It has a height of 4.
There
When
you
x
go.
equals 9, y equals 4.
That didn't quite match my picture here, so I'll just change the hash marks. Let's call this 9.
Okay.
So notice, as we talked about, it's always easier to adjust your hash marks to match your curve than to adjust the curve to match the hash marks. Okay, so we can use our graphing calculator to get the graph of this function. You could also do this by hand without using the graphing functionality, but I think your instructor will give you full credit if you just draw the graph any which way. Now, any ideas about how we can proceed?
Yep. So the question wants us to evaluate the integral in terms of area. So we can find the area between the x-axis and the function. So we have 2 triangles. We can take the area of both triangles. So 1/2 of 5 times 5 plus 1/2 of 4 times 4. That gives us our area.
Good. It would be good maybe to label this 4 since it's not there in the picture. We've seen in the past it's easy to plug the wrong numbers in. So we can say this here is 4 and that's 4. Sometimes that helps to avoid confusion. Did you get an answer?
20.5. Yep, 20.5.
So what's the answer to the question?
The area is 20.5.
That's right. How could we check this now on the calculator?
We could take the definite integral.
So let's give it a shot.
Second calc. 0 to 9. And we get 20.5.
Now, this is a good example of how, in this case, our answer is actually better than the calculator's. We got the exact answer. The exact answer is 20.5, but because your calculator is just drawing a bunch of Riemann sums, it only gets an approximate answer. Usually the approximation is so good it seems like it's exact, but in this case, I'm not sure why the Riemann sums didn't work. Maybe it got lazy and it only did 10,000 rectangles when it should have done 100,000. So anyway, in this case, our answer is actually better, but you can certainly see they're pretty darn close to each other. Okay, good. Okay, good. So that's another type of problem that you can see on the test. One of the most important things here is not to confuse this question with the other types of questions you might see. So now there's like 3 or 4 different types of questions about integrals. They might ask you to approximate the integrals by drawing maybe 5 or 4 Riemann rectangles. Or they might ask you to express the integral using the limit and the sigma notation. Or they might ask you to evaluate the integral exactly by using high school geometry. That's what this is. We used high school geometry to get this right. Notice this is an exact answer, not an approximation. Or what's the most common type? The most common type is just use antiderivatives to find definite integrals. That's what they normally mean. That's the normal way to do it. So you have to kind of ask yourself what type of question it is. If suppose they had just said, we wouldn't know how to do this one using antiderivatives, but suppose they had just said evaluate this. If they just say evaluate this integral, period, then they mean you to use antiderivatives. We only did the areas because they mentioned that. Okay, very good. All right, I think seems like you had some good intuition for that. Let's take a look at this then. Okay. Well, I guess you can give this a shot on your screen. If you get stuck, I'll give you some help.
Okay, so we're going from -3 to 3. I'm trying to look at the graph properly. Zoom. Fit, maybe? No, it's Y values. Zoom standard. There we go. Okay. Okay, so need to find the area. So area equals pi r squared. So our area is pi. This length is 6. Half of it's 3. Divided by 2. Okay.
So what's the answer?
The area is 9 pi divided by, 9 over 2 times pi.
Good.
Or, yeah.
Or the first way you were saying it would be correct too. 9 pi over 2 or 9 halves pi. Either of those would be okay. Now, that's good. Now, they didn't quite ask you for the area, though. What did they ask you for? I'll put it back on my screen.
Evaluate the integral by interpreting it in terms of areas.
So what are they asking us for?
An expression.
Maybe that was a weird question. They're asking us for this integral. They're asking us for the definite integral of the square root of 9 minus x squared between -3 and 3. But what's the graphical interpretation of a definite integral?
The area. And
it is an area. So what is this definite integral? What's the answer? What is this definite integral?
9 halves pi.
All right. So my only point is, instead of saying area equals 9 halves pi, our final answer should say the integral equals 9 halves pi.
Okay. But I used the right approach.
Oh, yeah, absolutely.
Okay,
I'm not sure whether the grader would be picky enough to care about that or not, but we've seen there are some cases where they were pretty picky. So I'm trying to be picky, too, as a defensive measure.
Right.
So anyway, your approach was very good. That the area is 9 halves pi. So it's true that the area is 9 halves pi, but technically the problem was not asking us for the area, it was asking us for the integral figured out by using the area. So the best way to write your final answer is like this. The area is 9 halves pi, so the integral is 9 halves pi. And this is an exact answer. The integral is the exact area, and we calculated the exact. So though now check that on your calculator.
Okay. But it would be wrong to try and take the definite integral of this. That would be incorrect, right?
I didn't follow you there?
So if instead of using the area approach, I use a definite integral approach, if I could even do this, that would be incorrect.
I think you're thinking what you're thinking is right. You didn't quite phrase that correctly. You said you should not use the definite integral approach, but
right.
We did find the definite integral. What you're thinking of is we should not use the antiderivative approach.
Okay.
So one way to find a definite integral is by using high school geometry to figure out the areas. And that's what we did here, because that's what they asked us for. Another way to work out this definite integral is by using antiderivatives. And you're right, we shouldn't do that because they told us not to do that here. Also, you're right, we haven't learned how to take this antiderivative yet. You and I haven't gone over this yet. So even if we could, we don't know how to do this antiderivative yet. So yeah, so I think that's what you were thinking of. Yeah, they don't want us to use the antiderivative method here. They want us to use this alternative approach. And the whole point here is they're just trying to give you a better feel for what definite integrals mean. They want you to feel, to get a feel for the idea that definite integrals are areas under curves. Okay. Did you check that on your calculator?
Yep, I got 14.137, and I guess I could double check that and take 9 divided by 2 times pi, and I should get that same number, and I do 14.137.
Let's see. Okay, yeah, so they come out to be almost exactly equal to each other. Okay, it's because the calculator is just approximating. Good. Okay, so that came out to be correct. Okay, so basically you did that correctly. That was good. We hadn't quite done a question just like that before, so it's good that you worked out how to do that. Like I said, just watch out in the test to make sure you're answering the right question, because now we have lots of different things, lots of different questions that we might have to answer on these types of problems, but I think we're getting those ideas down. So
just a quick question. So
yeah, sure.
So if I was using the antiderivative approach and I found out the answer was 14.13721, should I re-express that in terms of pi?
Probably, yes.
Okay.
Yes, that's right. So I believe that if you actually we haven't done it yet. This problem this problem is probably too hard for your course. I was saying you were going to learn how to do this in section 5.5, but even in section 5.5, this would be still too hard for you, I think. Your class was not going to learn how to do this. But if you did learn how to do this, you would learn that it involves the inverse trig functions. And remember that the output from an inverse trig function often includes what?
Pi.
So that would be the signal to divide by pi to see what your answer was. All right, but this problem is a little harder than you'll need to ever do in your class using antiderivatives. Your class isn't getting to this. All right, but you're right. To give an exact answer, we'd have to divide by pi. Okay. That's one of the advantages of using this high school geometry approach. With the high school geometry approach, we all already knew there was a pi in the answer.